The artificial intelligence sector has transitioned. System-level scaling has replaced raw compute as the primary metric for training performance. The prevailing logic over the last decade was simple: acquire more raw compute, add more GPU flops, and expand language model parameters. But as cluster sizes grow beyond 100,000 nodes to support next-generation multimodal training, the hardware-first approach reaches its limit. At the 100,000 node scale, observational data proves that synchronization, not raw hardware power, dictates the total performance of the system. Simply adding GPUs is no longer the highest leverage solution. The physics of massively distributed compute demand a structural intervention at the orchestration layer. Distributed AI workloads require constant synchronization across thousands of independent nodes. Operations like all-reduce generate intense east-west network traffic to aggregate model updates. This dynamic creates the compute utilization loop. Deploying more GPUs to the cluster generates exponentially higher communication overhead across the network fabric. This chart compares theoretical linear scaling against reality. Instead, actual empirical performance severely dips into superlinear cost growth as clusters expand. This widening gap represents wasted compute. The hardware is running, but processors are stuck waiting for data. The industry response has been to throw even more hardware at the problem, which only thickens the traffic and compounds the congestion. Until the specific compute utilization loop is resolved, the massive capital required to train large-scale AI will hit an insurmountable economic barrier. The root cause of this paradox occurs at the micro level during critical synchronization phases, known formally as the straggler problem. If a single data packet is delayed on a congested fabric, thousands of expensive GPUs are forced to sit idle, waiting for the update to arrive before they can proceed. Addressing this bottleneck requires a specialized architectural layer, the Predictive Tensor Control Plane, or PTCP. Classical software-defined networking is reactive, blindly pushing data into emerging traffic jams. PTCP, by contrast, assesses the global network state by compressing telemetry using a pattern-of-life tensor train. We see the difference here. On the left, classical routing forces data into collisions at central nodes, creating a backlog. On the right, PTCP uses CVAR geodesic routing to predict congestion and execute bypass paths before bottlenecks ever form. Anticipating the traffic flow drastically reduces the latency of data movement across the entire cluster. By successfully eliminating those network stragglers, PTCP ensures that overall GPU utilization remains near its absolute maximum capacity. The result is a direct mathematical correction. It shifts the cluster's efficiency curve away from superlinear degradation and back toward near-linear scaling, regardless of how many nodes are added to the system. Data routing is only half the equation. The other half is global state management. And here, classical SDN controllers reach a hard structural limit. As system complexity passes 100,000 nodes, coordination collapse occurs. Legacy controllers break down because they attempt to track these systems using continuous space grids. The processing overhead required to maintain that continuous mapping leads to degraded synchronization, unpredictable latency, and total system coherence failure. The solution to exascale state management is Tensor-Network Quantum Gravity, or TNQG, an orchestration layer engineered for emergent coherence. Instead of tracking a continuous space grid, TNQG maps the global system state using discrete tensor network entanglement. This discrete mathematical approach completely removes the debilitating processing overhead required by legacy systems. TNQG provides the foundational orchestration necessary to make hundreds of thousands of distributed machines operate as one unified system. The engineering efficiencies generated by PTCP and TNQG translate directly into economic impact, altering the ceiling for capital leverage across the stack. Consider the concept of latent capacity. Right now, between 20 to 40% of physical compute power sits idle, wasted purely by poor network coordination. Capturing that lost compute power presents a $1 trillion arbitrage opportunity for the hyperscalers who deploy these tensor-native frameworks. This document outlines the hierarchy of leverage within the AI infrastructure stack. While Tier 4 compute hardware remains essential, it is capital-intensive. Without an optimized overlay, raw hardware faces severe commoditization. The highest leverage point sits at Tier 1, the system coordination layer, where PTCP and TNQG operate to multiply the value of the underlying assets. Structural economic power has shifted away from raw hardware manufacturing and into the tensor-native system software layer. This structural advantage triggers a powerful economic feedback loop, effectively executing the Jevons paradox at a macroeconomic scale. By ensuring near-linear scaling and reclaiming massive latent capacity, these frameworks directly and permanently lower the base cost per AI token. Demand in the AI economy is highly elastic. Driving down the cost of compute drives exponentially higher market usage and rapid application development. This capital acceleration matrix assesses how these interventions impact economic metrics. By mitigating bottlenecks and reverting to near-linear efficiency, PTCP makes AGI clusters financially viable. Resolving these constraints acts as a growth multiplier, expanding the total addressable market for AI. System-level orchestration now dictates the value of global AI infrastructure, making tensor-native coordination the primary driver for capital efficiency in the coming decade.